Hello students, this is Professor Chalai, and in this video we're going to look at intermolecular forces. You can follow along using our Chapter 10 workbook. By the end of this video, you should be able to describe the types of intermolecular forces, sometimes called IMFs. You should be able to identify the types of intermolecular forces in various molecules, and also associate these intermolecular forces to various physical properties. Let's get started. In our previous chapter, we looked at gases, and so it only makes sense that we finish off this semester by looking at the other two states of matter, liquids and solids. And in order to understand how liquids and solids work or behave the way they do, we need to understand what we call intermolecular forces. So far, we've looked a lot at the intramolecular forces in molecules, and intramolecular forces are simply the forces within the same molecule. So within the same molecule, there we go. So we looked at this when we talked about the types of bondings between atoms when they come together to form molecules. For example, covalent bonding or ionic bonding or metallic bonding. Intermolecular forces, on the other hand, is forces that hold two different molecules. So this is between different molecules. So two molecules, we don't care what types of bonds they have necessarily, but what are the forces that hold two different molecules together? So here's an example of that. An intramolecular force is for example, the bonds that hold these molecules together, whereas an intermolecular force are the force holding those two molecules together. So intramolecular forces are often going to be very, very strong, right? They're chemical bonds, so they're very strong. Whereas an intramolecular forces are comparatively weaker. Now, there's a few types of intermolecular forces that we're going to look at, and they all have various different strengths. The weakest of these is what we call London dispersion forces, or sometimes just called dispersion forces. Now, if we scroll all the way here, we see that London dispersion is exhibited by all molecules. Regardless of what they are, all molecules will have London dispersion forces. The amount that they have, though, and the strength of it will depend on the type of molecule. So what is London dispersion forces? Well, let's look at it. Sometimes this is called van der Waals interactions, by the way. So if we look at a molecule, let's say it's a helium atom. So that's the nucleus, and it has 2 electrons, right, in an s orbital going around it. The orbitals give us a probability of where those electrons are, but it doesn't tell us exactly where those electrons are at any one point in time. And in fact, those electrons do often move about. So for example, let's say that we have one electron here at some time and another electron here. They're on this end of the molecule, so you might suspect that there's just a slight negative charge over there, and over here where the electrons are sort of missing, there's a slight positive charge. But maybe a second later, these electrons move about such that, I don't know, one electron's over there and one's over here now. Now there's no slight negative charge or a slight positive charge anywhere, right? And this happens for all molecules. So if you imagine, I don't know, a big molecule like this with, let's say this is let's say this is CH4. It's a good example. So we have carbon, hydrogen, 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 right? We have sort of the electrons, and I'm just drawing this very crudely, spread over some surface of the molecule, and any one point in time, these areas where the electrons could be or not be are going to have tiny, tiny changes in positive or negative charges, depending on where the electron actually is at that instant in time. And so if you have another molecule right next to it, right? Let me draw that other molecule like this. I know it looks really bad, but this would also have some tiny, tiny positive and negative charge on it. And so those tiny negative and positive charges would attract each other very weakly, but they would attract each other. And this is what we call dispersion interaction. Now, as you might be thinking, the larger the molecule, the stronger the dispersion interaction. The smaller the molecule, the weaker the dispersion interaction is. Really, it's more than just size, it's the surface area. Like the larger the surface area around the molecule, the more interactions, the stronger interaction. And here are just some examples of molecules that have similar sort of size, but because there we go, because the surface area here where these two molecules can interact is larger than this one, the dispersion force in this molecule is larger than its neighbor, even though they have similar number of atoms in them. So dispersion interaction depends on the surface area around the molecule because of those tiny, tiny little changes in electron density. Because of that, while dispersion forces is the weakest of all the ones I'm going to talk about, you could actually have very strong dispersion forces if you have very large molecules with very large surface area. But in general, dispersion forces or van der Waals interactions are the weakest interactions, intermolecular forces that we're going to study. In fact, you may have heard, or may not, that geckos are able to walk along walls and ceilings because of exactly this interaction. While it might be the weakest intermolecular force, if you have a very large surface area with lots and lots of dispersion forces, it can become strong enough to, hold a gecko upside down on the ceiling, for example. Okay, so that's London dispersion forces. The second weakest interaction that we're going to look at is dipole-dipole interaction. And it's exactly what it says. So let's say you have a molecule with a dipole moment. Water is a good example, right? OH. There we go. H. We know that oxygen is slightly more electronegative. This has a bent structure. So the oxygen will pull electrons towards itself away from hydrogen, such that there's a net dipole moment in oxygen sort of in that direction. The oxygen has a slightly negative charge and the hydrogens will have a slightly positive charge. Right? This is bigger negative and positive charges than in the London dispersion forces. So you can imagine there could be another water molecule here with the same slightly negative and slightly positive charges, right? And so a negative charge from one end of a dipole can attract a positive charge on another end of the dipole. And so this is what we call dipole-dipole interactions, right? We have a dipole here, we have a dipole here, and well, they're interacting. So these dipole-dipole interactions are going to be stronger than London dispersion forces generally, right? Unless you have a very large molecule over here. But they only happen for molecules with a dipole moment. So to figure out, while all molecules will have London dispersion forces, only molecules with a dipole moment will have dipole-dipole interactions. Okay, let's go on to another type of bonding. By the way, here it is. Polar molecules will have dipole-dipole interactions. Okay. Next up from that is what we call hydrogen bonding, also slightly stronger, which is slightly stronger than dipole-dipole interactions. Now, hydrogen bonding is even more specific, right? It only happens for atoms that have molecules where hydrogen is bonded directly to either a fluorine, an oxygen, or a nitrogen. So if you have a molecule where a hydrogen is bonded directly to a fluorine, oxygen, or nitrogen, well, what do you know? Like water, right? It could exhibit hydrogen-hydrogen bonding. So what happened is, let's put another water molecule there. These lone pairs can help bond towards this hydrogen right there. So in the case of water will have London dispersion forces because all molecules have London dispersion forces. Water will have dipole-dipole interactions like we talked about earlier, and water will also have hydrogen bonding, or H bonding for short, right? So one molecule could have more than one type of intermolecular forces. In the case of water though, hydrogen bonding is the most significant one because it's stronger than dipole-dipole interaction and it's stronger than London dispersion forces. I'm going down this list in order of strength. So as I keep going down this list, the interactions get stronger and stronger. Okay, let's look at the strongest one that I have on this list, which is ion-dipole interaction. Similar to dipole-dipole interaction, but instead of, but one of the molecule is an ion. Now, in examples that we're going to use in class, this rarely comes up, but this is the type of interaction between an ion and a dipole, as exactly as it says. So let's say you have, NaCl dissolved in water into Na plus and Cl minus. So I could have an Na plus floating around, and what else is there? Well, lots of water molecules, right? And I just mentioned that water molecules have dipole moments, where the oxygen will be slightly negative. So in all of these cases, we have an attraction between the ion and one end of the dipole. If it's a positive ion, it'll be attracted to the negative end of the dipole. If it's a negative ion, it'll be attracted to the positive end of the dipole. But because this is not just a tiny charge, like we wrote for the dipoles, but a full charge, the interaction is going to be even stronger. This one sort of rarely pops up, but in the cases that we will study in this class, but I wanted you to be aware of it nevertheless. So as I mentioned, the same molecule could have multiple types of these interactions. In fact, all of them will have London dispersion forces. Now, I mentioned that we needed to talk about intermolecular forces if we want to talk about solids and liquids. And the reason for that is we know that in solids, the molecules are held together pretty rigidly. In gases, they're zipping around with very little interactions between them. And in liquids, it's sort of somewhere in between there, where there's reasonable interactions between the molecule. So as you would suspect, as the intermolecular force increase, remember intermolecular forces are the forces holding two different molecules together, you're gonna tend to form solids. If the forces are weaker, you're gonna tend to have gases. So understanding what intermolecular forces exist in molecules will help us to understand whether they're going to be solids or liquids or gases, or even sort of what their boiling points will be. So let's look at a few examples. Let's look at number 1, where we have group 14 elements, right? Bonded to hydrogens. We have CH4, SiH4, GeH4, and SnH4. And the question here is, let's try to order them from lowest to highest boiling point. So the one with the highest boiling point, remember boiling is to go from liquid to a gas. So the highest boiling point here means that the intermolecular forces are stronger, so it takes more energy to turn them into a gas, the gas phase, to break those intermolecular forces. This is what this arrow is telling you. You need to add more energy to break those intermolecular forces through heat or temperature. So the stronger your intermolecular forces, the higher your boiling point, the higher your melting point, right? Because it's harder to go from a solid to a liquid. So let's look at these. We looked at CH4 before in class, and we talked about how CH4 does not have, is not polar, for one. It doesn't exist hydrogen bonding, right? So let's go over to the list here. We know there will exist London dispersion. It does not exhibit dipole-dipole interactions because CH4 is not polar. It doesn't exhibit hydrogen bonding because that's only for hydrogen when it's bonded to fluorine, oxygen, or nitrogen. And there is no ion in there, so there's no ion-dipole interactions anyway. So the only interaction that CH4 will have is London dispersion forces. In fact, all of these will only have dispersion interactions. So how can we separate them? Well, I mentioned that earlier that dispersion interactions, the strength will depend on the size of the molecule, or more specifically the surface area of the molecule. So we just need to order these in terms of size, because the larger molecules will have the higher boiling point, and the smaller molecules will have the smaller boiling point. We can ignore the hydrogens in each of the case because hydrogen is in every single one of them, and look at the other element. In this case, it's carbon, silicon, germanium, and tin. And we will find that carbon is the smallest radius atom, followed by silicon, followed by germanium, followed by tin. In fact, the same order that I have it written. So because of that, tin will have the highest boiling point, followed by germanium, followed by silicon, followed by CH4, which is methane, which is actually a gas at room temperature. So to answer these questions, what do? We first need to figure out all of the interaction forces, the intermolecular forces that these molecules exhibit, and then order them by their strengths, right? In these cases, we look at these types of interactions first in terms for strength, and then if we can't separate them by these interactions, we look more specifically at the molecules themselves. I hope that makes sense. Let's try numbers 2, 3, 4, and 5, and 6 on your own. Pause the video, and then when you unpause, we'll go over them together. Okay, so we have hydrocarbons for number 2, C2H6, 3C3H8, and C4, there we go, C4H10. So if I were to draw these, C2H6 would look something like this. And if you keep drawing them, all I'm doing is going to be making the carbon chain longer and longer. But I'll stop at just 2 of these to show you what's going on. Okay, so let's go through the list from strongest first. Do they have ion-dipole interactions? No, there are no ions in there. What about hydrogen bonding? There's only carbon and hydrogen, so they can't have hydrogen bonding. Dipole-dipole interactions, CH bonds are all non-polar, so those molecules are not polar. So they only have London dispersion forces. So in this case, again, we go straight to size. And I don't even have to draw the structure for us to figure out the size. This is the smallest, followed by this, and then this. So it'll be C2H6, followed by C3H8, followed by C4H10, because they only exhibit dispersion forces. Or dispersion interactions. Let's look at number 3. If you haven't, please try it on your own first. So we have N2 or CO. So N2 will have a triple bond if we did the Lewis structure. CO, similar situation. Let's look at intermolecular forces that each of these exhibit. Nitrogen will not have ion dipole, will not have, what's the one right below that? I already forgot. Hydrogen bonding, will not have dipole-dipole interactions, so it will only have dispersion. CO does not have ion-dipole interactions. It does not have hydrogen bonding because there's no hydrogen in it, but it does have dipole-dipole interaction because we know that oxygen is very electronegative, so it'll be slightly more negative than carbon. And so in this case, we'll have dipole-dipole interactions. So because of this, CO will have a higher boiling point. Let's write that. CO will have a higher boiling point. Okay, let's look at number 4. Try it on your own first, and then we'll go over it together. So we have 2 different molecules here. We have ICl and Br2, like that. They each have a single bond, and you can complete their Lewis structure like this. Now, in terms of size, chlorine is smaller than bromine, but iodine is larger than bromine, so it's hard to figure out which one might be larger than which based on just size. But let's look at their interactions. Well, they don't have ion-dipole interactions or hydrogen bonds because there are no hydrogens, there are no ions. But ICl will have a slight, if tiny, dipole moment. Why? Because chlorine is slightly more electronegative than iodine. In the case of bromine here, they're both equally, they have the same electronegativity, so there's no dipole moments here. So this will have some dipole-dipole interactions regardless of how small, whereas this will have just dispersion. By the way, in all of these cases, they will have dipole-dipole interactions and dispersion, right? So this will have dipole-dipole interactions and dispersion. Everything has dispersion. Everything has dispersion, so the others are all. But in the I'm focusing more on the dipole-dipole interactions because that's stronger than dispersion. So ICl will have the higher boiling point. Okay, let's try number 5. In number 5, we have dimethyl ether, ethanol, and propane. And they give us 4 different boiling points, but we don't know which one's which. And they want us to match each one with their correct boiling point and give reasons for it. So the best way to do this is to draw the structures of these and then try to figure out what kind of interactions they'll have. So for dimethyl ether, we have CH3 like this with an O and then another CH3. Right, and oxygen will have 2 lone pairs. So this is a bent geometry. Ethanol will be CH3, CH2 like that, and then CH2, oh, and then OH here. There we go. And then finally we have propane, which is just CH3, CH2 like that, and then another CH3. H. There we go. So let's look at this first molecule. No ion-dipole interactions, no hydrogen bonds. None of the hydrogens are attached to either fluorine, oxygen, or nitrogen. The oxygen here is attached only to carbons. What about dipole moments? Well, it does have a dipole moment, right? Oxygen will pull on electrons a little bit more than carbon, and it's a bent structure so that it doesn't cancel out. So this will have dipole-dipole interactions. Dipole, dipole. It will also have dispersion because everything has dispersion. All right. What about ethanol? Well, ethanol doesn't have ion dipole, but it has hydrogen bonding. A hydrogen is bonded directly to an oxygen. Let me put my lone pairs there. A hydrogen is bonded directly to an oxygen, so you will have hydrogen bonding, or I'll just put H bonding. It will also have dipole-dipole interactions because this oxygen will be more electronegative and therefore pull on electrons a little bit more, so it'll be a slightly negative charge. So it will have dipole-dipole interactions. And then, as always, everything has dispersion. Okay, and now let's look at this guy over here. No ion dipole, no hydrogen bonding, no dipole-dipole interactions, only dispersion. So, only dispersion, this should be the weakest, which means this should be the one with the lowest boiling point, which is negative 42.1 degrees Celsius. Second weakest would be dimethyl ether, this guy right here, and so this should be negative 24.8 degrees Celsius. And hydrogen bonding is stronger than all of them, so this one should be 78.4 degrees Celsius. And there we have it. Finally, let's look at number 6. Again, if you haven't done the video first, please pause the video and then we'll go over it together. So we have ethane, and they give us the melting point and a boiling point. They want us to predict whether methylamine, and they give us the structure, will be higher or lower than that of ethane, the melting and boiling points. So let's draw ethane. There we go, put all my hydrogens. And let's draw the methylamine. So CH3HHN has a lone pair there, H. Okay. This guy on the left, we've done a few like these before. It has nothing except dispersion. Dispersion. What about this on the right? No ion dipole, but here's a hydrogen and another hydrogen bonded to a nitrogen. Once we see that, we know this has hydrogen bonding. It also has a little bit of dipole-dipole interactions because nitrogen is a little bit more electronegative than hydrogen. So dipole interactions, and everything has dispersion. So in intermolecular forces, in this guy, right, the one on the right is a lot greater than the one on the left, and so this should have higher melting and boiling points. So to summarize this section, we talked about 4 intermolecular forces: London dispersion, which happens in all molecules and atoms; dipole-dipole, which only happens in polar molecules; hydrogen bonding, which only happens in molecules with hydrogen bonded to either fluorine, oxygen, or nitrogen, and ion dipole, which only happen with mixtures of ions and polar compounds. The order here is the strength is weakest for a London dispersion and strongest for ion dipole, and it goes down this way. And molecules could exhibit more than one type of intermolecular forces. The strength of the intermolecular forces determine whether these are going to be solids or liquids or gases and what their boiling and boiling points are. Okay, in our next video, we're going to talk more about the properties of liquids in terms of these intermolecular forces. We'll see you then.